Greetings from the Department of ECE, SJBIT. In this session, we will be learning about memory allocation, addresses and operation, followed by addressing modes, instruction set, instruction sequencing, and other topics. So first we will start with the module 1, second part, in the part B, part A itself, the second part. Memory allocation, addresses and the operation. So if you look at the memory addresses, one second. So memory, as we all know, that it consists of many millions of storage cells. Each cell can store a single bit of information. So how it will be stored and how it will be arranged means data usually accessed in n bit groups. So where n we call it as a word length. Now you observe, suppose this is a memory location. You have n bits which are stored in each and every memory location. So this we call it as a location, each location. So first location, this is a second location. Each location, let us consider, it can store a one word of data. One word means 32-bit data. Suppose if it can store a 32-bit data in one memory location, likewise n number of memory locations are arranged sequentially till to the last word. Now if I want to fetch the data present in this location or in any other location, I need to know the address of this. The address of this, if I know, then only I can fetch the data from that location. In order to fetch the data or in order to store data, I need to know first the address of the memory location. So that depends upon how many memory locations that I have. Suppose if I have 2 memory locations, so likewise that is 2 memory locations. So if I want to give the address uniquely, I can make use 1 bit. So 0 I will allocate as the address of first location, 1 I will allocate as the address of second location. Similarly, if I have 4 locations, suppose if I have 4 locations, if I want to address each and every memory location uniquely, then I will make use 2 bits starting with 00, 01, 10, 11. So like this, suppose if I have n bits as the address to be specified, then you will get 2 power n locations. Or to avoid confusion, if I say if I have k bits, then I can have 2 power k memory locations. Uniquely I can address. In each and every location I can store n bits of data. It might be byte or it might be word or it might be half word. So we will see that. Suppose if I say we are storing a data of 32-bit length. So you can see the example. This is bit not first bit, second bit, and so on up to this is a 30th bit and it is 31st bit. It means it is 31st bit and it is 32nd bit. Each and every 8 bits we call it as 1 byte. So if I observe, I have 1, 2, 3, 4. So 4 bytes constitutes 1 word. 4 bytes constitutes 1 word. Usually each 8 bits will be used to represent an ASCII character, American Standard Code for Information Interchange, ASCII, as you know. So this is how it is represented, and in the data the last bit which is meant for providing the sign. Suppose if the last bit is 0, usually we say that the number which is positive. The last bit if it is 1, the number which is representing a negative number. So this is meant for sign in case of signed arithmetic, and the remaining portion which is representing the magnitude. Last bit is for sign and the remaining portion is for magnitude representation. Now if as I already told you, to retrieve the information from memory you need either one word or one byte. Address of each and every location you need. Without address I can't fetch the data, or I can't write the data into the memory location. Suppose if I have k bit address memory, means you have 2 power k memory locations, or you can say if it starts with 0, 2 power k minus 1 memory space. Suppose let us consider if I have 8 bits, k means k if I consider as 8 bits, 2 power 8, which is nothing but 256 memory locations. Similarly if I have 10 bits, so 2 power 10 is nothing but 1 KB memory location. Suppose if I say 2 power 20 bits, 2 power 20. So you can also write this as 2 power 1 into 2 power 10. So it is 2 into 2 power 10 is 2 KB, not 2 power 10, sorry. So 2 power 10 into 2 power 10, 1k into 1k, so which is 1 megabyte, 20 means. Suppose if I have 2 power 24 bit memory location, I can say that it is meant for accessing 16 megabytes of memory location. How can it be? Means 2 power 24, I can write it as 2 power 10 into 2 power 10 into 2 power 2. So a power m into a power n plus n, 2 power 20 into 2 square. 2 square is 2 power 4. 2 power 4 is 16. So 2 power 20 means this is 1 KB and this is 1 KB. 1k into 1k, 1 mega into 16. So 16 megabytes of memory location that you can access. Similarly 32 bit means 4 gigabytes of memory location. 1 terabyte means 2 power 40 bits that you need. This is about the address and the data how you will store in a memory location. So while storing, as we all know that we can't store all 32 bit data at a time, and it is impractical to assign distinct address to each and every bit memory location. The most practical way how they do is byte of a data is addressed. So usually we say that byte addressable memory. Each and every byte can be addressed separately, that means uniquely. Byte locations can have addresses like 0, 1, 2 and so on. Word, as I told, which is of 32 bits and constitutes of 4 bytes as one word. Successive word addresses will become, suppose if it starts with first word address 0, second word 0, 1, 2, 3, all these 4 bytes which is meant for addressing only one word. Next address starts with 4, next 8, then consecutively keep on add 4 for this, which gives you the word address of the word addresses in a memory location. Now coming to the assignment of data, that means alignment of data, how the data will be stored in a memory location, which is in 2 forms. It can be in big Indian or little Indian assignments. So coming to big Indian, lower byte addresses are used for the most significant bytes of the data. Suppose if I have the data as 1, 1, 2, 2, 3, 3, 4, 4. This is a one word data which I wanted to store it in a memory location. So all these, this is a first byte, so this is a lower one, second byte, third byte and fourth byte. So these 4 bytes, how it will be stored? This is a lower byte address, this is a higher byte data, lower byte data, higher byte data, more significant byte of a data. In case of big endian, lower byte addresses, that means this one, lower byte addresses will use it for storing the most significant bytes. That means here I will store 1 1, then 2 2, then 3 3, then 4 4, like this. Suppose if it is a little endian, lower byte addresses will be used for storing the lower byte of data. So I will store it like this: 4 4, 3 3, 2 2, 1 1. How you are storing the data? That based on that you have two notations. One is big endian and little endian. Lower byte usually, which is meant for storing the lower data, lower least significant byte of the word. So usually little endian is preferred compared to the big endian in most of the cases. So addressing order of the bytes, word alignment, as I already discussed this part. Suppose as the memory is byte addressable, so first memory location address is 0, next memory location 1, 2, 3 and so on. Suppose if it is a byte addressable, word addressable, these 2 bytes are used for storing 1 byte. Next 2 is meant for storing second byte. Next one for storing third byte. If it is word addressable, first 4 bytes are used for storing 1 word. Similarly so on. If it is a 64-bit double word, 8 bytes, first 8 bytes will be used for storing 1 double word. So that's what 16-bit word means 0, first address is 0, second address is 2, next address is 4 and so on. If it is 32-bit word address, first address is 0, second address of the word is 4 and so on, 0, 4, 8 and so on. If it is 64-bit, 0, 8, 16 and so on. So it depends upon how much data that you are storing in the memory location. So majorly we have with respect to memory 2 operations, one is load and store. So ARM processor works based on load and store architecture. So load indicating loading the data, from memory to the registers. So from memory you are reading the data or fetching the data, or you can also say that copying the content from memory location to a register, whereas store indicating writing the data into the memory. Registers you can make use to store the data. Coming to the instructions, sequencing. Basically in any processor, must and should, it could be of any of these operations that it can perform. It could be data transfer between the memory and the processor registers, or it could be arithmetic and logical operations on the data to be performed, or it could be program sequencing and controlling operations like branching, looping instructions, or it could be I/O transfers like transferring between input and output devices. So these are the operations any processor, if you consider, must and should that you need to perform. So this is about the notation, how they will use for giving the representation in assembly language. So if it is a memory, usually they will write it as a LOC, location. Content present in that location, if I want to specify, square braces. Registers were specified like R0, R1, R3 and so on. So this indicating content present at R1 and content present at R2. That means R1 is holding the address actually. So in that memory location, the contents whatever you have, that will be added with the memory location at whose address is specified by R2. Content in that location will be added and it will be stored to register R3. So if I write like this, then we call it as a RTN, register transfer location notation. So another one we have is Another one we have is assembly language notation. So in CO we will make use this notation. MOVE meant for move, ADD is meant for adding, and it is in this direction. Process is in this direction. So this is source and this is destination. So content present in that location, memory location, has to be copied to register R1. Here R1 content will be added with R2 and to be stored in R3. So coming to CPU organization. So in CPU you have a single accumulator which can be used to store the result after performing arithmetic and logical operation, and you have a general purpose registers which are used to hold the in between to hold the operands, to reduce the, mainly meant for reducing the memory traffic, and register bookkeeping. Then you will have a stack. So operands and results, sometimes if you want to store, you can store it in a stack. These are the instruction formats. It is about a three address instructions. So you can observe here three address. Content of R2 and R3 were added. Result will be stored in R1. If it has to be specified in two address, same addition operation, R2 contents are added with R1. Result will be stored in R1 itself. This is the destination. If it is a one address instruction, then content of memory location, other operand will be, if they didn't specify anything, it should be an accumulator. Content of memory then is added with accumulator, result again stored in accumulator. If it is zero address, meant for usually the stack operations. Top of the stack and top of the stack but one, that means below to that, is added, result is stored in the top of the stack. So next we have is RISC instructions. There are lots of registers. Memory is restricted to load and store instructions. So this is an example of evaluating A plus B into C plus T. First you perform operation A plus B, then you perform operation C plus T, multiply both. So addition, then multiplication. This using a 3 address, similarly using a 2 address, this using a single address, and 0 address operations. 0 address means it's meant for stack, load and store. Then using the registers, as I already told you, registers are meant for storing the operands, which is to avoid memory constraints. So they are faster, shorter instructions that you will have. You can speed up the operation and minimizes the frequency with which the data is moving back and forth in between the memory and processor registers. So coming to the instruction sequencing, there are two types in this, majorly straight line sequencing and branching. So coming to straight line sequencing, suppose if I write a program, that program will be stored in a memory. Memory, as I already told you, you have an address and you have the data or the contents. So this is the data which you are storing it in a memory location. These are the addresses. Suppose in the instruction you have some of the operands which are again stored in a memory location. So you can specify these are the locations where the data is stored for the program. So there are 3 instructions in the program segment. So you have 2 operands which are stored in a memory, and the result which is again stored in a memory data area. This we call it as a data area, and this we call it as a program area. In the memory itself there are different segments. So you have a segment like data segment, program segment, and stack segment, like this. Here the assumption is each memory location, one memory operation is performed for one instruction, and all are of 32-bit word length. Memory is byte addressable. That's the reason why first memory location address is I, second memory location address is I plus 4, incremented by 4 bytes. So I plus 8 and so on, byte addressable. And full memory address can be directly specified in the single word instruction. There are majorly, while performing the operation, two phases which involves. One is fetching the data, second one is executing the instruction. So fetching stage and execution stage. First you need to fetch this, then execute the instruction, decode it and then execute it. Suppose if I want to perform n numbers, if I want to add n numbers, same instruction, you see, first one, number 1, which you are moving it into R0. Next you are adding second number with the result in R0. Next you are adding third number. Next you are adding fourth number, fifth number, sixth number, seventh number, and so on up to n numbers. Suppose if n is 2, then fine, only 2 instructions I have. Suppose if n is 100, I have 100 instructions to write. Suppose if I have n as 1000, I need to write minimum of 1000 instructions. And you observe all these 1000 instructions. Suppose if I have the numbers which are stored in, again, data area, this is data area, I need to fetch the instruction, I need to fetch the operand, and again I need to store that result to one temporary register. All these operations which I need to repeat, same operation I am repeating it. Instead, what I am doing here, if it is a sequential instruction, one after the other, which I will be writing, say as the same operation which I need to perform for more number of times, what I can do, I can initialize a counter. If I'll initialize a counter, I need to do it for 1000 times. If I want to do it for 1000 times, first time if I perform, I'll decrement by 1. Next time if I perform operation, I'll decrement the operation by 2, and so on. I'll keep on decrement the counter till that counter becomes 0. I'll keep on check. In the loop, I'll be performing only one operation. So same adding a n number example, I'll have one register to store the count, and I'll be adding the numbers in this loop. In the loop again, I'll be decrementing the counter till that counter becomes 0. I'll keep on repeat the same process. If this is greater than 0, indicating I need to perform the same operation, I'll go back, repeat the same operation. See the number of instructions which it has got reduced compared to the sequential execution. So what we are trying to do here is branching to a label called loop. So this is a label, we call it as branching to a label called loop. Branching to a new location. We are changing the sequence of execution. Sequential execution which I am changing by posing some condition on the branch. So I am checking the condition. If that condition is true, then I will go to a branch label called loop. Otherwise not. So that condition checking, for condition to check, we have a conditional codes or conditional flag bits. So there are 4 conditional flag bits which are supported by the ARM processor. One is negative, 0, overflow and carry. So different instructions will affect the different flags. Suppose if the result is negative, last bit, MSB bit, if it is 1, indicating the number is negative, then negative flag bit is enabled. Upon performing ALU, arithmetic or logic operations, suppose if the result is becoming 0, 0, then 0 flag bit is enabled. Suppose if I perform the addition or any operation, arithmetic operation, if the data is exceeding the size of the data, means if it is 32-bit, performing a 32-bit addition, if I add two 32-bit numbers, if it is exceeding, then magnitude, if it is exceeding that 32-bit size, then overflow flag bit is enabled. Then suppose if I am, upon adding two numbers, if I am getting any carry out of it, then carry flag bit is enabled. So based on checking the result of arithmetic or logical operation, one can write the branch instructions. So these conditional flag bits will be checked and it will be put to a new location. That is, sequential execution will be altered with the conditional checking. That we can observe, we can see in the programming part. So this is an example of conditional how the conditional flag bits will be enabled. Suppose let us consider these two are the operands which are present in A and B, two registers. Let us consider I wish to add these two numbers, A minus B. I need to subtract these two numbers. If I want to subtract, I will take a 2's complement of this number, take a 2's complement of that number, then add these two. So if I add, I am getting this result. Based on this result, I can cross verify. So 1 plus 1, if I add, I will be getting 1 carry. So carry flag bit is enabled. As the result is not 0, 0 flag bit is disabled. And the last bit is negative 1, indicating sign flag bit or negative flag bit is 1. As the result is not exceeding, overflow flag bit is 0. So we will be checking these conditional flag bits and then performing the branching operations in some cases. Now coming to the addressing modes. So how do you give the address of a, so how do you route? How do you specify the address of the operand? Based on that, there are different types of addressing modes. So they indicate about specifying the address of the branch target, or they can give the memory operand address directly in a single add instruction in the loop, or using a register to hold the address of the number 1 or passing it to the loop. So basically, addressing mode defines the way in which the location of an operand, is specified in an instruction is referred to as an addressing mode. So there are different addressing modes. Basically, you have an immediate addressing mode, a register addressing mode, direct, indirect, indexed addressing mode, base plus index and offset, relative, auto increment and auto decrement. So coming to one by one, immediate addressing mode. How we are specifying the address of the operand. In case of immediate, directly you will give the value. Operand itself is specified in the memory location. For example, I will be writing like move R0, hash 0x0005. So that means this is immediate data which will be moved to register R0. Coming to next one, register addressing mode. In register addressing mode, you will be specifying the address in the register itself. Then coming to direct addressing mode. In the direct addressing mode, location address itself is specified in the memory location directly. The effective address is the location, memory location. In case of indirect addressing mode, indicating in the memory you have a data. Suppose I have XX in the memory location as 99. This location address 99, if it is specified in the memory directly in the instruction, then we say it is direct addressing mode. Suppose this address is specified indirectly, like it could be stored in register R1 holding the 99, that will be used as an address to copy, or it could be the location address 99, content in that will be copied, effective address. So or it could be in case of indexed addressing mode. Suppose if it is if you are having a 10 and 95, so 95 plus 4, if I add base plus index, this is my place, how many times do I need to add to get the location address? Then it is indexed addressing mode. Base plus index. Effective address in this case is X is the base address. Content of array, how many times that I need to add, will be specified in register to get the effective address. So this is a base plus base with indexed addressing mode. base itself will be in one register, index will be in another register. Effective address to get, you need to add both base with index and offset. So x will be, one register will be holding the index, one register will be holding the base, and offset, if I want to add, I can add by x value. Coming to relative addressing mode, it is with respect to PC, program counter. In case of conditional branch or unconditional branch instructions, we go with PC. Auto increment and auto decrement means I have the content, so means one memory location I have content. After copying the content, memory location address has to be incremented automatically. So first it will copy the content, then increments. In case of auto decrement, first it decrements the counter and then copies the content. So these are the ways of specifying the address of the operand in the instruction. It could be an immediate value directly. The operand itself is specified in the as an immediate value, or it could be stored in a register. The operand itself is stored in a register, or the operand address is directly specified, or the operand is indirectly specified either in register or in location address, or the operand address is calculated by adding with a base. Effective address is specified with a base, and it could be base with index and offset. If it is branching through PC, value can be incremented. Then auto increment and auto decrement cases, automatically counter, if it has to get incremented, you can go with the auto increment and decrement operations. So this is what effective address, how do you calculate, deriving the effective address. So in the addressing mode, as we have seen, TOS specifies top of stack, AC indicating it is a accumulator, implied addressing modes. So in case of immediate, as I told you already, we'll make use #05, R1. Immediate data is moved to register R1. This is an immediate addressing mode. In case of register addressing mode, R1 will be holding the address. Then move R1, R2. It's an example of a register addressing mode. This is a direct addressing mode. Address of that is directly specified in the index. Next one is the indirect addressing mode. So here you can observe, if I have written like add content of R1, R0, R1 is holding actually the address. See, address, it is holding the address. The content will be there here. Then it is holding the address, that the address present content present in that address is an operand that will be copied over. So it is in case of indirect addressing mode. See, A will be holding the address, this is an address. B, A will be holding the address, so that this address, content present in that location will be an operand. So this is an indirect addressing mode. Work means addition of n numbers. You will be having a counter, how many numbers to add, first number, address of the first number, clearing the counter, then you are adding the content of R2 with R0. This is a buffer. Pointer will be incremented, decrement the loop, and condition checking. If not, go back. So this example of adding the numbers again, writing it in a different manner. Take an example of applying for 5 numbers. So effective address already I told you. In case of addressing effective address with base indexed addressing mode, x plus content of Ri, offset. So x of Ri, effective address will be x plus Ri. If it is base addressing, base with index B, this is the one holding the base address, then another one holding the offset. This is an example of offset given as a constant. Offset is in the index register. Now see here, you can observe. So 20 comma means the content of R1. R1 is holding this. So from that you need to add 20. You will get the operand address. Whereas here 1000 will be having R1 is holding a 20H. You need to add 20, then you will get this location. Here it is with the index register. Here it is given as a constant. So this is an example for index addressing modes with indexing in an array. See here, you can observe base address plus relative address. Suppose if I have base means relative address as 2, base address as 100, these two will get added. You will get the address of actual content. So this content will be copied over. This is an example for showing finding sum of marks of all subjects. This indexed addressing mode, instead of given specifying it as a constant, I can specify that even in register. So these two contents will be added and will be holding the data that will be copied over. This is with respect to PC relative addressing mode. PC content will be added with the program counter content will be added with the constant, then that will give you the address of the operand. So coming to additional operating modes, there is an auto increment. Automatically it will get incremented. First it will be contents will be added with R0, then a pointer will be incremented automatically. So next we will see about the assembly language. In assembly language, a few things like mnemonics, which is representing the symbolic names like load, store, add, move, all these things. A complete assembly language means a complete set of such symbolic names and rules for their use as a programming language. We call it as an assembly language. So we will be specifying the syntax of it. Then we have an assembler. Assembler already we know, which can be automatically translated into a sequence of machine instructions. Assembly language instruction, which is converted into a machine instructions by a program called as assembler. It is a collection of utility programs that's a part of system software. Suppose if I write the user program in original alphanumeric text format, that we call it as a source program. The assembled machine language program, we call it as a object program. So in an instruction we have a opcode, operand or the addresses. So opcode, these are the operands, and suppose in some cases if I specify this as an address. So there are assembler directives. Apart from mnemonics, you will have some directives which are meant for directing the assembler to perform some operation. So it could be like 20 equals to EQU is an assembler directive, equals to 20. Wherever you find with the TWENTY, it replaces with 20 by the value as 20. So even here see sum means equals to 200. Wherever it finds sum, it replaces with 200. These are a few things which you can easily find out. Suppose in case of immediate addressing mode, if it is a decimal number, directly you can write. If it is a binary number, you can specify as ampersand, percentage followed by the binary number. If it is a hexadecimal, hash dollar symbol, or some cases hash 0x. So these are the type of instructions. These are data transfer instructions. You have load, store, move, exchanging input output, push pop. These are for stack and these are for IO operations to move. These are for loading and storing with respect to memory, and this is for registers, exchange with the registers. So the same thing with different addressing modes. How do we can write for load and store? These are arithmetic and logical operations. So you have logic. These are set of logical operations that it can support, then arithmetic operations that it can support. And these are control instructions, program control instructions like branch, skip, call, return, compare and subtract instructions. These are conditional branch instructions, digit indicating branch if 0, non-zero. Upon performing arithmetic and logical operations, based on the result, the conditional flags will be enabled. Depending upon that result, the program counter will be branched to a new location by specifying this. Branch if carry is 1, no, carry is not set, positive, negative, overflow, non-overflow. So with this we have completed till assembly language programming. Next session we will start with basic IO operations. Thank you.